So what in the world does a bulletproof vest have in common with the electrical grid that's powering your screen right now? I mean, on the surface, absolutely nothing. One is stopping a very real physical threat to one person. The other is this massive, sprawling system that keeps our entire society running. But underneath it all, they are both built on the same idea, an invisible blueprint. A series of incredibly detailed technical documents and standards that allow our super complex world to function safely. In this explainer, we're going to pull back that curtain and see how these hidden blueprints literally shape everything around us.
Here's how we're going to do it. We'll start with the raw, intense process of testing body armor. From there, we'll zoom out and see how that same kind of thinking protects enormous industrial systems. Then we'll look at how it's shaping our green energy future. And finally, we'll get to the foundational manuals, the instruction books that basically run our modern world.
All right, let's dive right into something pretty intense, body armor. How do you really know it's going to work when it absolutely has to? Well, the answer isn't just a guess. It's laid out in this incredibly detailed document that outlines the meticulous, and I mean meticulous, science of stopping a bullet. See, testing a vest isn't as simple as just shooting it and seeing if the bullet pops out the other side. It's a science, and it's all about statistics. The key idea here is something called the ballistic limit, or BL. Now, this isn't a pass-fail grade. It is the exact speed where a specific bullet has a 50-50 chance of getting through the armor. It's a statistical knife's edge that tells engineers precisely where the armor's performance limit is.
But you know, stopping the bullet is only half the battle. You also have to survive the sheer force of the impact. And that is where this next term comes in, back face signature, or BFS. When they test armor, it's mounted on a big block of clay that mimics the human body. The BFS is the dent the vest makes in that clay when it gets hit. It's a direct measurement of blunt force trauma. A deep dent could mean broken ribs or severe internal injuries, even if the bullet never even touched you.
The actual test itself is a brutal gauntlet. First, they condition the armor. It gets tumbled around, baked, soaked in water. Basically, they simulate all the wear and tear of being used out in the real world. Then, it's mounted on that clay block in a super controlled lab. Shots are fired at exact spots, at specific angles, and at precise velocities. And after every single shot, they meticulously measure for perforation and the depth of that all-important back face signature.
And this, right here, is where the true power of standardization really shines. Different types of armor are rated to stop different kinds of threats. So a Type 2A vest gets tested against a standard 9mm round. But a Type 3A vest, that has to stand up to a much more powerful .357 SIG, or even a .44 Magnum. Having the shared standard means an officer anywhere knows exactly what level of protection they're getting. It's a common language for safety.
Okay, so we've got a rigorous, repeatable, scientific system to protect one person. It works. But how do you take that same level of thinking, that same rigor, and apply it when you need to protect thousands of people in a factory or a whole city's power supply?
This is where we have to shift our thinking a little bit, away from personal armor and into the world of system safety. The goal isn't stopping a physical bullet anymore, it's preventing a catastrophic failure in a process. The focus shifts from materials and impact dynamics to system architecture and reliability. But the core idea? It is identical, using a strict, documented standard to guarantee things work when lives are on the line.
And that brings us to Act 2. We're taking that life-or-death rigor we saw in the ballistics lab, and we're applying it to these incredibly complex industrial machines, where a single tiny failure can be just as devastating.
Now, in the industrial world, they don't talk about armor types. They talk about safety integrity levels, or SIL. A SIL rating is just a standardized way of measuring risk reduction. So just like the ballistic limit measures the statistical chance of a bullet getting through, a SIL rating quantifies the statistical probability of a safety system failing when you need it most. It's the same math, just applied to a totally different kind of threat. This whole concept is written down in standards like IEC 61508. The IEC, that's the International Electrotechnical Commission, basically creates these global blueprints for engineering certainty. Their goal is to create a complete plan for the entire life of a system to make sure it doesn't just work, but that it fails safely, that it can diagnose its own problems and stop them from ever turning into a catastrophe. And if you're wondering why this level of detail is so important, just think about this. An arc flash, which is basically an electrical explosion, from a pretty common 480-volt circuit, can have the same explosive force as 8 sticks of dynamite. That's the kind of power these standards are designed to contain, every minute of every day.
So now, let's scale up one more time. We've got from protecting one person to protecting one factory. But what about protecting the entire planet's energy system as we switch over to renewable power?
The scale of this challenge is, well, it's hard to even wrap your head around. By 2050, the world is expected to need almost 39,000 terawatt-hours of electricity. And to make that happen, we'll need to get about half of that enormous number from renewable sources. This isn't just a simple upgrade, it's a complete reimagining of how we power the world.
And what makes this so complex is that the old model of how we get power is being totally thrown out. As this quote explains, we're moving into a world of prosumers. Energy is no longer a one-way street from a big power plant to your house. Now, your home with its solar panels, your office building, your local factory, they can all produce, store, and even sell energy back to the grid.
This new model is sometimes called everything as a grid. It's a messy, decentralized, two-way network where energy is zipping back and forth all the time. Your neighbor's solar panels, the wind farm across the state, the battery storage at the grocery store, they're all active players. And trying to manage that incredibly complex, constantly changing flow of energy requires a huge layer of digital intelligence and control.
And this is where it all comes full circle. That same disciplined, standards-based approach used to certify a safety switch in a factory is exactly what we need to manage the energy grid of the future. The stakes are just as high, and the need for proven, documented, rock-solid reliability is absolutely essential.
So for our final act, let's look at the bedrock that all of this is built on. Because the vests, the factories, the grid, none of it just appears out of thin air. It all exists because of documented, shared human knowledge. What is the one thing that connects all these dots? Well, none of this incredible engineering is even possible without our ability to write it all down, to share it, and to build on it together. That shared knowledge is the ultimate invisible blueprint.
It all starts with the fundamentals, the basics of software engineering. This is the logic, written down and standardized, that runs everything from a factory's control system to the digital brain of our entire energy grid. It's the language that all these systems use to talk to each other.
And it also depends on clear principles of traceability. These documented processes are what let us track every single part in a supply chain, from the specific batch of fiber in a bulletproof vest all the way to a critical sensor spinning inside a giant wind turbine. It's how we guarantee quality and find problems before they cause a failure.
And, it requires a deep commitment to ethics. Because when you're writing the manual for a life-saving piece of equipment or the documentation for a nationwide power grid, being clear and accurate isn't just about good writing, it's a moral responsibility. Any ambiguity could have devastating consequences.
And ultimately, it demands that we get better and better at communicating all this research visually, so that this complex, vital information is easy to understand for everyone who needs it, from an engineer on the factory floor to a policymaker who's shaping our future.
So, from the specific weave of a vest to the lines of code that keep our lights on, our modern world really does run on these invisible blueprints. They're the manuals we write for ourselves to manage complexity and to keep each other safe. And that leaves us with one final big question. As our world gets even more complex, what is the next critical instruction manual we're all going to need to write?